Thanks for coming. We are fortunate today that we have special guest, Nathan Myhrvold. He is our collaborator on asteroid research, working with Joachim Moens, our grad student, and Mario and myself. And he'll tell us a little bit about his research today, but he is one of the most interesting, most impressive people I know. So he's working on many different fields. He started college as a very early little boy, much earlier than normal. He ended up with degree, PhD in physics from Princeton. He worked for a while as postdoc for Stephen Hawking. Then he decided to go back to industry, IT industry. Among many other things, he was the founding director for Microsoft Research Lab. Then he got bored, he retired when he was much younger than I am now, and then went back to science, and then did many different things in science. He became world expert in dinosaurs, for example. He became world expert in physics and chemistry of cooking. He published a beautiful book, actually 5 books together, Modernist Cuisine. Just recently he published Modernist Bread, which is also 5 big books. He introduced it to me as the greatest book ever written in human history about bread making. Being trained as a scientist myself, I took it with a grain of salt. But then I looked through the books. It tastes better that way. Exactly. That's one of the points. So I looked through it. I think it's probably correct. It's a very serious book. But I will not take any more time from Nathan. So today he'll talk about his asteroid research, some interesting results that taught us many things, not just about asteroids, but about scientific process today and how we can improve it. Please.
Okay, great. Well, it's a pleasure to be here because I wouldn't have wasted all this time on asteroids if it wasn't for Zelko and my collaborators here, initially because of interest in LSST. So the WISE project, or the WISE mission, was an infrared space telescope. It was launched initially with the goal of just making a map of the heavens in the infrared, but it was used to make a number of asteroid observations as well. In fact, this has allowed the NEOWISE group to publish diameter and albedo measurements on about 164,000 asteroids. Now that's more than all other sources combined prior to that. In fact, I think it's 16 times more than all other sources combined. And it's a treasure trove of data. We're very unlikely to have anything else like this soon. There is no currently planned or proposed mission that will have a 4-band infrared look at asteroids. And because it is this giant amount of data, and the best we're going to have for many years, it's important to understand what's in it, what are the strengths, and what are the weaknesses. So anyway, I undertook this study and tried to sort of understand what was all there. It's a little complicated because the first segment of the mission, where a whole lot of these papers are about, was in the full cryogenic phase. Initially, they thought they would have a year where they had a cryogen that was cooling their IR detectors, and during that year, they could get this information. Well, for reasons no one has quite figured out, that year turned into about 8 months. The frozen hydrogen ran out sooner than they would like. So it was during that period, the full cryo period, that they were able to measure all 4 bands. Then there was a very short period of time when they had 3 bands. That lasted a month. And then since then, they've only had 2 bands, the W1 and W2 bands, which are shortwave enough that the ambient temperature of space isn't a problem. The other ones, of course, is a problem. So besides those original papers, the NEOWISE results are also available on the Planetary Data System, and so this is an archive of all of them. This was put up in 2016. Now, one of the things that I discovered is that although this is already complicated because there's different mission phases and different asteroids, you can't actually take all of the things that are there for granted. It clearly says here it's a compilation of previously published diameters, and here it was entirely by referencing results previously in the literature. Now, that's important because there's about 800 papers that reference the original publications of the NEOWISE group. So they used the data in one way or another. And so it's really useful to know, has that data changed in this compilation? The documentation says it hasn't changed, but it actually has. So, for example, there's 3,772 asteroids that were in the original papers published in Astrophysical Journal, and they're just not in the PDS. That result is missing. There are 1,200 asteroids that are brand new to this PDS. I didn't mean to do that. They're attributed to this AppJ paper. The paper was from 2011, but they're not on the paper. And nor are they aliases. Sometimes there are two asteroids will be believed to be independent. Later on, they'll be aliased to discover, no, actually they're the same asteroid. That actually doesn't count. So there's pretty substantial differences. Asteroid 53, in the original AppJ publication, here are its parameters. A diameter of 115 kilometers, and this is the number of observations in each band. In the PDS, it has a much different diameter. Of course, different albedo and beaming. It's not surprising that those would change if the diameter changed. It has the same counts, so it's probably the same observation that's just now been recast, and we'll see why a little bit later. But the fact that's a round number is interesting. So that's a 27% change. This one here is a 35% change. Some are smaller, some are much larger, more than 100%. So the first point is there's been a lot of updates in this latest archive. Here's more of the things. Here's 70. And besides some of these things, when you see a much larger difference here, that's likely because there's some other effect going on. It's not just the diameter changed. Something else changed to make the albedo in the infrared band go from 1 to 0.04. Now, the NEOWISE results are often described as if they're a single uniform body of data, but they're not. In fact, there were 10 different models that were used in 12 different band combinations. And this was only possible to figure out because a code saying which model was used was introduced in that PDS archive. It wasn't in the original papers. Now, that would leave 120 combinations. They don't all exist. It's actually 47. And here they all are. And I'll sort of walk through them. 45% of them are what I call NEATM-like. NEATM stands for Near-Earth Asteroid Thermal Model. It's the dominant model that people use for doing simple asteroid modeling. Simple meaning it's not a thermophysical model that requires a shape up front. It's a much simpler one. And in the NEATM parameter, you try to derive the diameter, but you also derive what's called a beaming parameter, or the eta parameter. 55% are actually something like STM. STM is called the standard thermal model. The big difference between STM and NEATM is that STM assumes the value of the beaming parameter. Historically, they thought this beaming parameter thing was sort of a let's measure it once and we're done. And the initial measurement was on, I think, Ceres and Vesta, and they came up with a measure of 0.75. Well, now we know it goes all over the place, but more than half are actually STM-like. 44% of them are fully thermal. By fully thermal, I mean they have the W3 and W4 bands. Those bands are long enough wavelength that there's effectively no reflected sunlight, whereas the other ones are. And if you're doing thermal modeling, that's kind of the most important thing. So about 44% are actually thermal. These have one thermal band. 50.7% only have a single band of data. Now, that's interesting because you can't really do thermal modeling with a single band of data. The only way to work with it is to make a bunch of assumptions. So it's very analogous to saying, I know an object is dim. Is it small or is it dark? Well, if you assume you know the albedo up front, well, then you know. So these 50, more than half of the results, they made an assumption effectively about the IR albedo or the albedo in a particular band, and that assumption totally derives the answer. So I think it's more fair to call these a rescaled result than a real thermal modeling result. Whoops, let me go back. So a bunch of the combinations of bands and asteroids, bands and models are weird. So here we have asteroids which have only the W1 and W2 bands. These data points here, actually all of these that are in a box, are things that mean you're doing a fully thermal model. And if you're doing a fully thermal model, how do you do that with these two bands, which are only in the shortwave, where the W1 band is completely dominated by reflected solar radiation, and W2 is roughly 50-50 between emitted light and that. And so all of these cases are kind of weird. Here's where we see what the codes mean. So DVBI means each one of these things stands for a parameter that's determined by fitting a model. And the Needham model, as most people would understand it, is DVB. Now, the Needham model was originally invented in the context of long-wave thermal observations. In long-wave thermal observations, you don't care about reflected sunlight because it's negligible. Well, because two of the bands have substantial sunlight, that's why they had to add the I here. And that means they have to estimate what the albedo is in those bands. And that's an output of the fit. Now, a problem with that is that they didn't obey Kirchhoff's law when they did this. So the emissivity in the, say, W1 and W2 bands and the albedo in those bands have no relationship to each other. One is treated as a free parameter. And of course, Kirchhoff's law says that the two, yeah?
Can you just tell me what the beaming parameter actually is specifically?
Well, it's a fudge factor. So when they first started measuring asteroids in the infrared, okay, this is great. There'll be a temperature, and that temperature will tell us, we'll be able to fit a black body radiation to it, and that's great. And then people said, well, okay, actually the asteroid is curved, and so you'd expect you'd have some parts of the asteroid at different temperatures, but it's fundamentally like a black body. And the trouble is, that isn't the temperature you measure. I mean, sometimes it is. But this beaming parameter is effectively a fudge factor which makes up for the fact you measure the wrong temperature. Now, in the case of Ceres and Vesta, I said it was 0.75 is the beaming parameter. Well, that means the temperature that they measured was too high by a ratio of 0.75 to the 1/4 power, which, sorry, I can't do in my head. But it's a substantial difference. Now, when this came out that the asteroids are the wrong temperature, people said, well, what's going on? And a variety of effects have been used to describe this. One of them is that some of the infrared light is being beamed off in a preferential direction. And the best example of that would be if you see somebody driving tonight, or you're riding a bicycle and you're driving, the person riding the bike often has retroreflectors on them, little things which bounce back light. Now, they don't have an energy source. The reason they look so bright in your headlights is because they preferentially reflect light in a direction. So the argument with the beaming parameter is that the infrared light is being preferentially beamed in the direction of the sun where we can't see it. And so if we're off that, that would be a reason. Now, the beaming parameter can also be greater than 1. If it's greater than 1, that means the asteroid looks too cold. The asteroid's too hot. So how could that happen? Well, if you had an asteroid that had a very rough surface or lots of craters or lots of valleys, when it emits light, it may emit it and capture it again. And if you have light bouncing back and forth in some crack, effectively the albedo you'd see for that effectively goes to 1 or something close to 1 because it bounces back quite a bit. So that's what the beaming parameter, does that help? Typically, it ranges between about 0.5 all the way up to about 4. 3, or actually the value pi for the beaming parameter, is what you expect for an asteroid that is rotating very, very fast. And the value 4 is the value you'd expect if it was tumbling on 2 axes. Okay, here are the bands. I've been talking about the different bands. Here's the wavelength in microns, W1, W2, W3, W4. You can see this is at about 3. This is about 4 microns is the center. The W3 band is much longer, and it's really wide, and that causes some things. Here is 3 different examples with different values of the emissivity in the W1 and W2 bands. So you see here for the black curve, if you assume that the emissivity is about 0.9, which is a common assumption, what you discover is that the W1 band is essentially all reflected sunlight. That's what this line is reflected sunlight. And if you look here in W2, you see that across the band, the two are about the same, so it's about 50%. Now, this is a log thing, so it can go away from 50 pretty quickly. But the W1 is basically all reflected light. And then these show you at different values of the emissivity, of course, those trade-offs are different. If you have something which has low emissivity in the W1 band, like this one here, 0.3, you can see that the W2 band is also dominated by reflected sunlight. And the value 0.3 is actually not an unrealistic value. If you look at laboratory spectra of meteorites, some are as low as that. If you look at laboratory spectra of silicate minerals of the type we think asteroids are made out of, and of course we have a much larger collection of those than we have of meteorites, then you can go down to 0.1. Okay, so that's what that code meant. And these are the best, these are absolutely the best ones because we are using all of the bands. And we should expect only to do this when we have all of the bands. So then, if we have a dash in one of the positions, the dash means we're going to take it by assumption. And the main reason to do that is if you don't have enough data and you try to fit for all of these, you're over-constrained. So for about 70,000 results, you have to make an assumption about what that IR albedo is. You can't derive it directly from the data. This is a strange one. This says you're going to fit the diameter, but you've assumed everything else, including the visible band albedo, beaming factor, and and IR albedo, but that's still 1,000 asteroids that that's done for. Okay, so how do you make that assumption? Suppose you want to say, I want to make an assumption about the IR albedo. Well, this is the approach that they took. They said, okay, we will assume that the IR albedo is some multiple of the visible band albedo. And a typical value of A would be 1 or 1.5. And for each one of the NEOWISE papers that analyzed a different group of asteroids, say main belt or the Jupiter Trojans or Hildas or Neos, for each one they'd have a different A. Well, here's the problem. If you take all of their own results that fit the thing, so they presumably have a correct value for the infrared albedo and the IR albedo, it turns out it doesn't work very well to say that one is a multiple of the other. I mean, this has a vague trend that the two are related. The trend line isn't the line that they actually chose, but there's really substantial scatter. So you should expect that if you've used this as your assumption, you're going to have a much larger error in your whole model because the bands that are affected by that assumption could have a much different flux than you think. So here's, sorry, it's a kind of a dense thing. So for each one of these, here is the value that was assumed. So for this particular line, they assumed that that multiple A was 2 for the Hildas. If you look at the actual ones when they fit them, it goes from 1 to 3 with a mean of 1.94. That's not too bad from that. But then you could say, okay, well, what if I fit this line and say I'm going to fit the line PIR equals that? What is the correct trend line for those? Well, the correct trend line is not the mean, it's this 1.76. But then if you're going to fit a line like this, well, why don't you fit this line too? This line has a constant offset term. Now, there's no particular physics behind whether you use either one of these, but if you're going to fit this, it makes sense to try to fit that. And if you do that, you discover that you get a very different slope if you just have that constant offset. And then if you say which of these two is a better fit with the corrected Akaike criteria, well, you discover it's not even close. This one is vastly better. It's vastly better. Now, it's still really bad because you saw the scatter on the previous chart. So anyway, this is sort of similar all the way down. If you try to do a fit, in almost all cases, you'd be better off with the offset. And the slopes aren't even very similar. Yeah?
That's a quick question. Is there a physical reason why you would expect an offset in addition to?
Well, the argument for using a multiple of the visible band one was to say, well, we think these things are blacker in the infrared than they are integrated across the visible spectrum. That's the physical argument. The physical argument for an offset is to say, well, they're going to be blacker by a certain additive amount period before you get to some multiple. That would be the argument. Now, I say I don't believe the argument, and the data doesn't support the argument. But then you could say, okay, but did they actually use the values? So we say we're going to use the value of A equals 1.5. No, actually they didn't use that. So here's the paper that, and this is the majority of the asteroids here. This is 134,000 asteroids. We can see that the value 1.5, and this is only the asteroids where they say they use this assumption. Well, you can see that there's two things going on. First of all, this is a very broad thing here from 1.4 to 1.6. Then these blue ones go all the way down to 1. And the difference between the gold and the blue is that these are at that level because one of either the visible band IR, albedo or the IR albedo is exactly 1.0 in the results, which means I think they clipped them. So these were probably due to clipping, but the others, that width isn't. So although the paper says they're going to do that, it turns out that isn't the actual thing. Now, if you look down here, these papers do a much better job. They say they use 2, and pretty much they use 2. These 2 humps here are very low, and that's probably due to just rounding in the number of digits that they expressed each of the things. So some of the papers are pretty good. This one is pretty good, except for this, which is only 2 asteroids, but still. But most of the results are up here, where the actual assumption isn't followed. Okay, so then we have these. This is dv-I and dv-. This is the beaming parameter. So these are the ones where we're going to assume a fixed value of the beaming parameter. So let's see how those turn out. Well, here, sorry, it's another dense chart. If we go to this is the one that has maybe the most asteroids in it. If you look at what they assume 1, in fact, the mean over all of the ones that they pick is 1.02, so that's pretty close. And for 68,000 of them, they do use 1. But for 3 of them, they use the value 1.2. And each of all of these over here are the exceptions. You know, for this paper, it assumes 1.0, but in fact, there's 9 cases that use 1.2, and there's no other. Those are the only 9 that are in the case. And it's basically everything that's shaded differs from that. And so the commonality between this and the previous thing is that whenever there's a rule, it seems that there's a bunch of exceptions to the rule. And there might be a good reason for the exceptions, but it isn't documented. Here's another thing that was quite puzzling to me. If you get the raw observational data, you can say, well, how many asteroids did we observe at least 3 times in all 4 bands? And that's how many. Of the total asteroids observed, it's about 23%. So then you say, okay, great. So that means 23% of my models ought to use all 4 bands. It doesn't work that way. So of these asteroids that have all those bands, this is the number that were actually used with all 4 bands, and it comes out nets to 3%. So a huge amount of the 4-band data was discarded. And here we see what happened. So in these are the ones that were kept. So this has all 4. They used all 4, but only 13% of those went over there. 86.9. They threw away 1 or more of the bands of data. Now, how did that happen? Well, there's two reasons. The first is they insisted on dividing the analysis into 3 to 10-day epochs. So they would say if they were observing an asteroid, they would decide a 3 to 10-day period, and they would call that an epoch. But that was quite arbitrary. It's not a property of the asteroid. It's a property of where the asteroid is and the cadence. And some papers say 3 days, some say 10 days. Now, that's unfortunate because if you observe the asteroid in multiple epochs, in one epoch you might observe in all 4 bands or in 3 bands, and the other bit in 2 more. And I should say the reason you don't always observe. When you look at an asteroid with this satellite, a bunch of things may cause 1 or more of the data points to drop out. So that could be a background noise source. That could be because it was below a sensitivity threshold, or it could be that it was fully saturated and above a threshold. So as a result, although every observation was made with 4 independent sensors, they didn't always register a data point. Now, then they had this thing that I call the 40% rule. So within each epoch, they would count the number of data points. And whichever band had less than 40% of the maximum, they would discard the entire band. This shows some examples. So here's an asteroid where we have 158 observations in W4, 177 in W3, 108 here, but only 65 in W1. And since this is less than 40% of 177, you throw it away. But it's not particularly near sensitivity limits or any other reason. It's just thrown away because it's got the wrong count. Here's another example. Here's an example a little bit like this one, but here there's just enough more that they're not thrown away. Now, the reason they say they do this is due to cosmic rays. But I don't understand how cosmic rays could cause that. Now, a moment ago, I said that you don't always get all 4 bands. In fact, if you just tally the entire full cryogenic mission, this is the number of observations in each band. And you can see that, in fact, you have less than 40% for those, for W1 and W2, if you just took it all together. So if you treated it all like one epoch across all asteroids, you'd always throw away the 2 bands. So what that means is the observations where you have more than 40% are in some sense atypical. So, okay, so here's how do you determine the accuracy of asteroid thermal modeling? You're fitting your model, you think you know how much flux you get. Well, you compare it to what are known cases. And known cases are I and other people call a Ross diameter. That stands for radar, occultation, or spacecraft. Those are the 3 primary ways that you can determine the size of an asteroid. Radar is pretty straightforward. You bounce radar off of it from Arecibo and you see how big it is. Occultations, you time it going in front of bright stars, and from the time and the speed you can figure out the size. If you really care, you do that multiple times, and you do that across a geographic range that gives you multiple slices, and you can even get a shape model that way. And then, of course, for a very small number of asteroids, we've actually gone there. So we know Ceres pretty damn well by now, and Itokawa and a bunch of others. Now, at the time that NEOWISE published this in 2010, 2011, there's about 100 asteroids that we had. So it's a very small number compared to this overall corpus. But that's what we have to check the accuracy. But unfortunately, there's a problem. So this is the table from the paper that has the most asteroids in it. It's the main belt paper. And you can see all of these have 0, 0, 0 at the end, and these don't. Now, of course, you could get 0, 0, 0 just by numerical coincidence. But in fact, these correspond exactly to these prior Ross diameters. In fact, there's 129 estimates for 105 asteroids. And the chance of that happening purely by chance is 1 in 10 to the 210th, with actually very generous assumptions. So let's assume this wasn't by accident. And there's other evidence it wasn't. So this is just a table of examples. So for asteroid 19, in this paper by Massaro, this is the main belt paper. It has 223,000 meters. Well, that's the same as this prior paper. It's interesting that there also were other papers published before then that have different diameters for most of those asteroids. That's also one of the things, if we're going to pick one, how do you pick the one that you anoint as the best one? Now here's another strange thing. So you might say, well, now that was in the original 2011 time frame. Well, in 2015, I brought all of this to their attention. And in 2016, they put this PDS thing out, and it turns out that these disappeared. Now, as we saw earlier, the PDS says it's strictly a compilation of prior. And when they disappeared, new values are put in, and they were retroactively attributed to the previous papers. So this shows a set of them. In 84 cases, they just omitted a result. In 12 cases, they wound up putting these modified things in. But this is the most interesting set. 9 of the examples where there was a copy diameter actually were retained in the PDS, and they have a model code. And this is the model code that they have, -VB-. Now what that means is that diameter is not determined by a model fit, which means it had to be set to an assumption. So the fact that this model code exists means it wasn't an accident, so we don't have to worry about 1 chance in 10 to the 210th. In fact, it was one of the things. So they set this for those Ross diameters. So now you might say, well, why does this matter? And it matters because you can't actually determine the accuracy. If you try to determine it, you discover, whoops, the accuracy is perfect. This was in 2016 when this came out. A guy at UCLA, Jean-Luc Margot, asked, and Joe Massaro said, actually, yes, if the radar occultation diameters were available, they were used. It wasn't actually in the paper, however. Now, here's another interesting point. The WISE satellite was made to take a map of the sky. And when you make a map of the sky, you want to have overlap between each frame. So the overlap is roughly 10%. And since asteroids can occur anywhere in there, about 10% of the observations are observed twice within 11 seconds. They happen to be in this region, so that in between two things, you got to look at them twice. Now, Hannes et al. In 2015 realized, hey, this is a way we could verify what the standard deviation is on the flux. It's a great measurement of flux errors. And now, they did it for the W1 and W2 band and for 400 observations. I did it for all of them. So here, this is the flux measurements, and here you can see the number of pairs. So 17,000 pairs for W1. Here's 133,000 pairs for W3. And the x and y axis here are the measured flux. And so those ought to be straight line, perfect y equals x lines, but there's a bunch of scatter. Now, each of those observations also has an estimated error. This is the WISE pipeline error. Well, it turns out that varies a lot too. And if you think about it, that's stranger even than the flux varying. You expect that there's some error in your sensor, and that error in your sensor or in how the light hits the particular wells in the CCD, of course you're going to have some error. But it turns out the estimate of the standard deviation also changes a lot. And these boxes are the boxes that correspond to a signal-to-noise ratio of 11, and this is 4.7, I think. So it turns out it's also true for the best observations. Now, a different way we can do this is, here's those same things, but now I've colored it by this statistic. So if you were going to do classic statistics, you'd call this a z-test, and this is the z statistic. And we can then say for each observation, how many standard deviations out is it? If this was correct, then it should be 1. Well, you can see this goes out to 7 sigma. And here, if you look at the maximum standard deviation, we have some that are at 46 standard deviations out. Well, when you have 46 standard deviations out, it means something's really wrong. It doesn't mean it's really a random thing out that far. So, in fact, if you then take the z statistic for each thing and you map a histogram of it, the histogram isn't well fit by a normal distribution. The dashed line here is a normal distribution, and that's the best fitting normal distribution by maximum likelihood. So this black line is a student's chi distribution. Now, a guy named William Gossett, who is the head brewer at Guinness, was also an amateur statistician. And Guinness had a rule that you could not publish under your own name if you were an employee, so he published under the name student. Now, I went to Dublin to the Guinness Museum and Brewery, and I said, do you have anything on Gossett? And they said, why, yes, but you're the first person who's ever asked. And so they had like a picture of him because he was head brewer. And I said, but you don't mention his statistics. They looked at me like, what? The problem that Gossett was working on, or student was working on, was if you have a normal distribution and you take a small sample of that normal distribution, what are its properties? And so we all did this in statistics class eons ago. Well, it turns out that's what fits these, and there's a strong reason for that. The estimates of the flux error are derived entirely from the Poisson statistics of the fluxes. But in a single exposure, they don't have enough statistics. So it's not actually a good estimate of the standard deviation. It's a sample of that standard deviation. In fact, a sample that's almost exactly students' or Gossett's problem. His was a normal distribution. Here it's really a Poisson distribution, but it's close enough that that's the one that works. Now, the other thing that's interesting is that the standard deviations are much, much larger. So here, if we fit a best normal, you get a standard deviation of 2.4. And if you took the standard deviation of this, you'd get something even a little bit higher. So what this means is all of the hardware flux errors on WISE are misestimated. And they're misestimated by a large factor. It's a different factor for each of these sensors. And that's largely because the sensors were made to take an infrared map of the sky. Mostly they're looking at stars that are pretty hot. So the sensitivity of this W1 thing isn't really what you'd like for asteroids. It was an average sensitivity, as you have to have in a survey. So then here's the same thing if you say let's filter it by standard deviation. So we pick only the ones that have very high SNR. So this is sigma less than 0.1. That's SNR better than 7 for them. And not only is the effect still there, but in fact the effect is stronger. So as far as that was 2.4, that's 2.7. So this is a pretty big deal. So then the question is this something weird about asteroids? Or is it something weird about the edge of the sensor? And the answer is no. From Zelko, I got a list of 1 million stars that were used for the Sloan survey calibration. So they're thought not to be variable or not too variable. And so you can play the same game with those stars. The stars, of course, are hot, so they don't really have a lot of hits in the W3 and W4, but they're great in W1 and W2. And here you can see this is the ones that are less than 11 seconds. So those are the double observations. And these are the ones that are not there. Of course, there's about 10 times more of them. So these are elsewhere in the sensor. So it's not a sensor effect, and it's also not an effect that's specific to asteroids. Now, you might say, well, how could this happen? And I think the answer is that the WISE sensors and the whole mission was originally designed to do a map of the sky that would have 8 to 12 co-added frames at every position. Now, by the time you take that many co-added frames, the individual errors don't matter so much. The primary science part of the mission that uses a single exposure is NEOWISE. And they didn't effectively plot this to check whether the error would be correct. Now, whenever you do a curve fit, it's always reassuring to plot the original data and the curve that's supposed to fit it. And so here is a plot from one of the NEOWISE papers. You can see there's the fluxes, and here's the fit to it. And we expect the fit's not perfect because the NEATM model assumes an asteroid's a sphere, so it's going to be a little bumpy. Now, it turns out this is the only asteroid out of the 164,000 where this is plotted in any of the papers. I started plotting them, and I found a lot of them don't come even close to fitting. So here's an example here. This asteroid has 22 observations in each of the 4 bands. The NEOWISE curve is this red line. And you notice that it's, not only is it not a good fit, in fact, all of the residuals are of the same sign. It's entirely below. Here's another case. Now, in this case, that's not true. The NEOWISE fit is this line here, and this line does have a few residuals of another sign, but it's clearly not a really good fit. In fact, in both cases, the blue line is like an actual best fit. So I wondered, how frequent is this? And the answer is really a lot. Here it is by absolute numbers. Here it is by percentage. It might be easier to think of as percentages. So for the very best fits up here, that fit all 4 bands, 57% of them have residuals of mixed sign in all 4 bands. Now that still, it doesn't mean it's a good fit, but at least it has mixed sign residuals. So at least there's some data point above and some data point below. But that means the remaining 40-some% in at least 1 band, you have all of the residuals of a single sign. This is maybe the most surprising ones to me here. This is the W3 and W4 fits where you have a single band, and all of your data is based on that single band. 29% of the time for W3, all the residuals are the same sign. So the curve doesn't even go near the cloud of data points. And in this case, not only is that a high percentage, but if you can see here, it's a high absolute number. Because there's 70,000 fits there, so that's about 20,000 that don't go near.
So
Yeah?
Can I interpret that as saying that the data are insufficient to move the prior substantially? Whatever the prior assumptions were put in, the data were essentially insufficient to make the prior posterior, to make the posterior very different from that.
Well, that would be a fancy Bayesian way of saying it. I doubt that's what was actually done. A more heavy-handed way to say that is they put a constraint on. And the curve fit was done within a constraint, and it bumped up against the edge of the constraint. Certainly none of the papers discuss anything remotely like the sophisticated version, but it amounts to the same thing. The difference is if you make an assumption and that's your constraint, no amount of data will move that particular prior because it's not part of a feedback loop.
But it does sort of mean constraint in, constraint out, right? The data didn't contribute much to the final result.
Well, I think it contributed nothing, is what I would say. I mean, if you can't hit, if you have multiple bands of data, you can have the problem that your model is fitting in 3 bands and it's not fitting in the 4th band for some reason. And I even have some ideas what that reason would be. If you have a single band of data, this is like saying you can't take the mean of a cloud of points. So effectively, that to me says, but the question you could have asked is, how do I know if I'm calculating flux the same way they are? And this is how. If I take my way of calculating the flux and I apply this to all of the things, I sum up all of my residuals, or not sum up, but I histogram up all of the residuals in each band, this is what I get. So if I had a systematic difference in how I calculated flux, we'd see these way away from 0. Instead, we don't. And so there's apparently no systematic difference in how I'm calculating flux. This also says, for every time that a constraint has it below all the points, there's also another one where it is above all of the points. And it's approximately equal, as you can see in these. Well, here's another thing. The way you define visible band albedo for a spherical asteroid of a certain diameter with a absolute visible magnitude h is this, right? So that means you ought to be able to, if you, the NEOWISE results have the h value that they used, they have the diameter, they have the visible band albedo, so it ought to work. But it doesn't work. So here's how I do that. For each result, I plot the, you can view this as either it's a change in the albedo and the diameter is correct, or it's a change in the diameter and the albedo is correct. Of course, it could be somewhere in the middle, but that sort of gives you the goalposts. So if we plot the change in albedo versus this, you get this plot. If I then do delta PV over PV, this cloud sort of collapses into that, which I think is quite interesting. So we can see that in most of the cases, it works. But in 15,000 cases, it doesn't. And some of them are quite large. So here in 5,000 cases, there's more than a 10% change. In 100 cases, there's more than 100%. It's off by a factor of 2 in albedo. Or equivalently, if you go up here, the worst ones are off by about a factor of 4 in diameter. So again, there probably was some constraint that was placed so that these things don't work out. Okay, so then you might say, after all of this, can we compare to those Ross diameters and get an answer? Well, fortunately, since 2011, there's been a lot more Ross diameters that are out there. And so what you'd really like to be able to do is to compare this across all of the asteroids. The problem is, suppose you have this case, W1, W2, W3, W4. Well, if you had that case, you could also do all of the subcases by just forgetting some of the data. But they didn't do that. So in this case, there's 429 of these that have a Ross diameter result, and you find out they're not too terribly bad. There's a systematic error of about 4%. They're about 4% small. And it's plus, this is a confidence interval rather than a normal plus or minus, but minus 13 to plus 17. Unfortunately, most of the asteroids are not in this. The reason this has got so many is that the asteroids we have Ross diameters for are big ones or close ones. And big and close ones we tend to be able to see in more bands. So most of the asteroids are down here. For example, those ones with the single W3 band. Well, we only have 17 of those here. So it's hard, yet there's 70,000 in the result set. So it's pretty hard for me to say those 17 are a really good proxy for the 70,000. And you can see, if, as one would expect, when you go to these other models, you get both larger systematic errors, sometimes quite large systematic errors, and you get much larger random errors. Here are plots of, this is the NEOWISE versus the Ross ones. We can also look versus IRAS. IRAS was an earlier IR satellite. Or Akari, which is another earlier than NEOWISE IR satellite. And the colors here are different models or different band combinations. And the reason that's important is you can see that they're not all the same. In some cases, in this case here versus Akari, we can see that red, which is the DVBI, that's the best ones, those kind of are evenly distributed. But when we go to some of these others, like here, we can see that the models are systematically occurring in some places, either for certain sizes or certain amounts of deviation. So the conclusions here is that this data set is a fantastic data set, but it's not a solved problem. There's a lot more work to be done. Zelko and Jakob and I have been working, and Mario have been working on a project to address this. It's a big job because to redo all of it, not only do you have to run the software, but it's all of the weird exceptions, and I think there probably will be a bunch of weird exceptions. But I think this is important because there's the possibility you'll find some systematically interesting things. In fact, I think most of those examples where a rule had an exception, the exception was enforced by some constraint. And I think what happened is the NEOWISE people thought that constraint was really important. But there's a different way to view it. In science, if you get a really weird result, that sometimes means it's actually weird science. It's interesting. It's something that gives you insight not only into the weird case, but sometimes it gets you insight into all cases. So with that, I'm done. If there's any questions, happy to take them.
Thank you, Nathan. Looks like we ran out of battery, so we didn't record the last few minutes. So are there questions? Don?
So what's the uncertainty due to the unknown thermal inertia, which could vary all over the place? Depending on the way the liquid, whether you pull on or equator on.
So that's another really good question. I did some work on this for a previous paper, and there's two ways to look at it. One is you say, well, actually, I can absorb that in my beaming parameter. The beaming parameter, the reason I called it a fudge factor, is it actually will compensate for all kinds of different things. The obliquity, are you looking at the pole and it's rotating in a funny direction, which we know some of them are? Do you have an unusual thermal conductivity? If you had an asteroid that had a high conductivity, or more correctly, a high diffusivity, then you'd see a lower temperature on the surface because a bunch of the heat is getting transmitted down into the asteroid. And then on the night side, it can be removed. So that's what the beaming parameter is for. And most people would say, yeah, that's what's in the probably plus or minus 20% that prior to NEOWISE people would say was the typical error. NEOWISE claimed that there was much less than 10%. And as we've seen, it's probably closer to 20 for the best ones and much worse for the worst ones. So in a sense, the accuracy that I showed on the previous slide wasn't an unusual accuracy. That's more what people would expect.
Now, here's this free parameter because you can have asteroids at 0 ray width, asteroids are solid Y, and rare asteroids are actually metal.
Well, and so Alan Harris of Germany, who wrote, because there's two Al Harrises in asteroids. Al Harris of Germany, who invented NEDM, actually has a paper from 2014 or 2015 called How to Find Metal-Rich Asteroids that uses that beaming parameter. So he says if you've got an unusual beaming parameter, that's an interpretation of it, or a combination of that and knowing the spectral class of the asteroid. So I think you could get some something from that.
More questions?
Yeah?
Right.
What assumptions about the shapes of the asteroids?
So for normal NEDM modeling, you assume it's a sphere. Now, that's important for two reasons. One of the reasons, and I think this is one of the problems that the NEOWISE people got into, is most scientists sort of reflexively will use a minimum chi-square fitting. So they'll say, I've got my flux, I subtract from my my model from my observed, I divide that by my flux error, I square that, sum that, and that's what I use in this. Well, there's two problems with that. The first is the NEOWISE, or the WISE NEOWISE sigmas were wrong by a factor of more than 2 for some bands. So that gives you a problem. But the other problem is if you have a spherical asteroid and you have lots of these measurements, the light curve variations look to the algorithm just like their variations in the error. And what this does is it causes you to get a bad fit or the whole fitting thing to fail and get no fit. And it's well known that if you try to do chi-square with error values that are too small, you have a problem. So the variations away from the light, due to oblong asteroids rotating with some pole position we don't know, that variation can cause a real problem. If you had enough measurements, and for a lot of these asteroids you do, then you'd expect that would all average out. And the line would give you effectively the mean surface area. And you get the spherical asteroid that has the equivalent surface area of the other.
So asteroids are just like cows, they're both spherical.
Well, it turns out it's really, so there's been a big debate about, and one of the things, I have a previous paper to this on Kirchhoff's law and using Kirchhoff's law. Some people say, well, why do you even do a simple model? And the answer is, if you have 100,000 asteroids, it's really easy to screen with a model. And second, unless you have a shape model or some way of getting a shape model from really good observations in the visible, it doesn't actually help you. There's been a bunch of papers on that. You're just better off assuming it's a sphere and getting the equivalent sphere than make an assumption about an ellipsoid shape that's wrong.
Are there more questions? We are kind of beyond the limit of time, so if not, let's thank Nathan again.